We are still working our way toward that last axiom for real numbers. And in this video, we get the last two concepts to set us up for it. So we're going to be talking about infimum and supremum of a set of real numbers. First, we're going to review what lower bounds and upper bounds are, same as from the last video. We're going to refine our understanding of lower and upper bounds to understand how the endpoints of intervals work. And then that will lead us to defining infimum and supremum of a set of real numbers. And then we'll finally apply those definitions to an open interval. So recall from last time that if you have a subset S of the real numbers, we say that a real number alpha is a lower bound if alpha is less than or equal to every number in the set. We say that a real number beta is an upper bound of S if it is greater than or equal to every number in the set. And recall for the interval 3, 5 from the in-class activities, we looked at that interval in a few ways, looking at different lower and upper bounds. We noted that the set had many lower bounds and many upper bounds, in fact, infinitely many. But the number 3 was special among those lower bounds in that it was the largest of the lower bounds. And the number 5 was special among the upper bounds in that it was the smallest of the upper bounds. So that leads us to the following definition. If we have a subset S of real numbers and S is not empty, this does not work for the empty set. If S is bounded above, then a number beta is the supremum of S, also called the least upper bound. If beta is an upper bound of S, and any number less than beta is not an upper bound. In other words, all upper bounds are beta or higher. And then we write that as beta equals the sup of S. If S is bounded below, then a number alpha is the infimum, also called the greatest lower bound. If two things happen, alpha is a lower bound of S, and any number greater than alpha is not a lower bound. In other words, all the lower bounds are alpha or below. So then we write that as alpha being the inf of S. So note that there are sort of two parts to being a supremum and an infimum. You must prove that it is an upper bound in the case of supremum and lower bound in case of infimum. And you also must prove that any smaller number than the upper bound or larger number than the lower bound is not an upper bound or a lower bound. So in terms of our containment model, the supremum does not let any numbers get above it, right? It is an upper bound, but if you get any lower, you will lose containment. That means you are just barely ahead of your children. You're ahead of your children, that's as a good upper bound will be, but just barely. So for the infimum, it does not let any numbers get below it, right? You have containment, but if you get any higher, you will lose containment, which means that you are just barely behind your children. So let's verify the supremum and infimum of 3, 5. We already know what the answer is, but let's see how the proof is going to go. So for the supremum, we're going to show that the supremum of 3, the interval between 3 and 5, is equal to 5. Now we already proved that 5 is an upper bound. That just follows from the definition. Every number in the interval is less than 5, so that's an upper bound. Now we're going to prove that any number that is smaller than 5 is not an upper bound. So in terms of our containment model, we know that an upper bound means no number in the set is larger than an upper bound. But we want to know what it means to be not an upper bound, because we want to prove every number is smaller than 5 is not an upper bound. Not an upper bound means that some number in the set is larger, or at least one number in the set is larger. In other words, one of your children gets ahead of the adult. So let's assume x is less than 5, and what we want to do is show that x is not an upper bound. So we want to look for our lost child in terms of x, right? So the lost child is in the set, and it is greater than x. That means that lost child has to be somewhere between x and 5. Well, it might make sense to find the average between 5 and x, right? That'll be between x and 5. The question is, will that x plus 5 over 2 be a lost child? Has to be two things, right? Has to be a child. In other words, it has to be in the interval, but then it also has to be lost. It has to be, you have to lose containment for x. So let's look at x plus 5 over 2, see what the biggest it can be, what the smallest it can be. Well, we know that 5 is bigger than x, so if we replace 5 in x plus 5 over 2 with x, we get a smaller number, x plus x over 2. X plus x is equal to 2, you cancel the 2's, and that shows us that x is less than x plus 5 over 2. That is very promising, right? It's bigger than x, it has the potential for being a lost child. We also know that x is smaller than 5, so if we replace x with 5, we're going to get a bigger number. 5 plus 5 is 10, and 10 over 2 is 5, and so that means x plus 5 over 2 is less than 5. So that makes a really good argument that x plus 5 over 2 is going to be in the interval as less than 5. The only issue is that number going to be greater than 3? And if x is really small, the answer is no, it won't. So let's say the x is really small, like say 1. 1 plus 5 over 2 is 3. 3 is not in the set, so it doesn't count as a lost child. It's simply not a child, right? But it's not as bad as it looks, right? X plus 5 over 2 doesn't work in this case, but 1 is pretty small. It's in fact less than all the elements of 3, 5, so it will be easy for us to find something in the interval that makes things work. In fact, any number in the interval will work. So x can't be an upper bound because it's going to be way too small. So we're going to split it into two cases. One where x is less than or equal to 3. That's going to be easy, but it's necessary so that we don't have issues with the average being in the interval. So let's choose any number in the interval between 3 and 5. I'm just going to magically choose 4. Clearly x is less than 4. 4 is in the interval, and again, we could have chosen anything. There was nothing special about 4. That automatically means that x is not an upper bound. The case 2 where x is greater than 3, now we can use that average. We know that 3 is less than x, that's just our assumption. X is less than x plus 5 over 2, that was the computation we did on a previous slide. X plus 5 over 2 is less than 5, we also did that computation. And that tells us two things, right? X plus 5 over 2 is in the interval 3, 5, so it is a child, right? And x is less than x plus 5 over 2, so that poor child is lost, right? X is not an upper bound. So we showed that 5 is an upper bound. We showed that every number smaller than 5 is not an upper bound. That means that 5 is the supremum. Now we're going to play the exact same game with the infimum. It's going to be kind of a mirror image of the argument that we used for the supremum. So we're going to prove that the infimum of the open interval 3 to 5 is equal to 3. So for each x in 3, 5, x is greater than 3. That means 3 is a lower bound, so that works, right? Now we need to assume that some number is bigger than 3 and show that number is not a lower bound. So again, we're going to split it into two cases for kind of the same reason, to make sure that we don't get any numbers that are outside of our interval. So our case 1 is going to be x is greater than or equal to 5. And once again, we're going to choose just a random number in the interval. That'll make it work. We'll choose 4 again. Why not? X is greater than 4, and 4 is in the interval. That means that x is not a lower bound, right? It's not a lower bound because you have something in the interval that is smaller than it. Our case 2 is where x is less than 5. Now we can use the average between x and 3 this time. So 3 is less than x plus 3 over 2. X plus 3 over 2 is going to be less than x. And x itself is less than 5. And then that tells us two things. First of all, x plus 3 over 2 is in the open interval 3 to 5, so it is a child. And x is greater than x plus 3 over 2. That means x is not a lower bound, right? It can't be a lower bound if it's bigger than anything in the set. So we showed that 3 is a lower bound. We showed that every number bigger than 3 is not a lower bound. That tells us that 3 is the infimum. All right, so now after seeing that proof, I think you're ready for the activities for Infima and Suprema. Just go ahead and click on the link that's below this video.